So, captions in English, please. So this is the second video of chapter 4, and it will be about the atomic theory and the structure of the atom. So this idea of atoms became a scientific theory in 1808 by John Dalton, who devised the first atomic theory that said, each element is composed of tiny particles called atoms, and all atoms are identical within the same element. All atoms of an element have the same mass and properties that distinguish them from other atoms. Atoms combined in whole number ratios to form compounds. And atoms are indivisible in chemical processes. Atoms cannot be created nor destroyed in a chemical reaction. So this is the first atomic theory, and it has evolved since then because experiments have forced scientists to change parts of this theory. And so J.J. Thomson in the 1890s wanted to find out more what an atom looks like. And so by doing this, he discovered the first subatomic particle called the electron. So the theory was not correct anymore by saying that atoms were indivisible because they found that smaller particles make up the atom. And these are electrons. Electrons are very small, they have a small mass and are negatively charged. That's what Rutherford came to. And it was known at the time that atoms were neutrally charged. So we'll watch the video of how J.J. Thomson came to the discovery of the electrons.
It was here in Cambridge that the first clear evidence for smaller objects inside the atom was found. Many of the great scientists of history have walked these streets, and one of the greatest was J.J. Thomson, who became the director of this, the old Cavendish laboratory. In 1896, Thomson had just got his hands on this new piece of kit. Now, it's essentially a particle accelerator. When this plate's heated, particles are emitted. They're accelerated by these electrodes. They pass through these two plates across which you can apply a voltage, and they hit the end of the bulb here on a screen which glows so you can see the beam. Now this is a modern version of Thomson's apparatus. Again, we've got the particle accelerator and there's a screen in there so you can see the beam glow. What Thomson did was he varied the voltage across the plates and he measured the amount of bending as the voltage changed. That allows you to deduce the mass of the particles in the beams. Now, the lightest known particle in Thomson's day was the hydrogen atom. But Thomson found from these measurements that the particles in this beam are almost 2,000 times lighter than hydrogen atoms. Thomson had discovered the first subatomic particle, the electron.
The electron owes its practical utility to its smallness. It might apparently Shakespeare say, my use is great because I am so small.
The electron was the first discovery of a fundamental particle, and it is interesting to realize that more than 100 years later, the electron is still, to the best measurements we can do today, a fundamental letter of nature's alphabet.
We can use electrons as ways to probe materials and look at the structure in electron microscopes or in big machines like this accelerator behind me. Pretty much all of everything we do in the 21st century depends on understanding the properties of electrons.
Thomson had discovered that the atom is not the fundamental building block of matter. There are smaller objects inside. So atoms could no longer be thought of as hard, indivisible spheres. But how did the electrons fit inside the atom? Thomson suggested that the atom was something like this muffin, with the negatively charged electrons embedded in a positive body. It would be a student of Thomson's that proved him wrong.
So at the time of Thomson's experiments, the most common way to study electricity in the 1890s was to build a glass tube called a cathode ray tube. So it was made of a tube, a glass tube, where the air was pumped out. There were metal electrodes at each end of the tube, and one electrode was made of zinc sulfide. And there was a battery hooked up to the electrodes. And so when you would apply a current, you would see a bright glow. You would observe a bright glow at the zinc sulfide electrode. And it's only 10 years later that this glow was attributed to a stream of negative particles that are called electrons. So Thomson's conclusion from his experiments was that the mass of the atom is due to the mass of the electrons, because that's the only subparticle he knew at the time. Electricity has no mass. There must be a lot of empty space in the atom. Since the electrons are negative, it is assumed you must keep them apart so they will not repel each other, because like charges repel each other. So empty space where they would roam around. And it must have a positive charge to balance the negative charge of the electrons, because it was known that atoms were neutral. So you have to have a positive charge to balance the negative charge. But how these charges would fit together in the atom? So Thomson devised a model, and he called it the plum pudding model of the atom, where you would have the electrons like the plums or raisins in a muffin, embedded in a sphere of positive charge, the muffin. So that was his view of the atom. So Rutherford, who was a student of Thomson, and he adhered to the plum pudding model, and he wanted to prove it. So he put it under scrutiny in 1911. And he wanted to prove that plum pudding model. And so the question was, how can you prove that something is empty? And the answer was, put or shoot something through it. And so use large target atoms, so very thin sheets of atoms, so they do not absorb the bullet. So large atoms, target atoms. And then for bullets, use very small particles with very high energy, so that they would not be affected by the electrons. They would be small enough compared to an atom, but bigger and higher energy than the electrons. So the bullets that Rutherford used for his experiments were alpha particles. Alpha particles are due to radioactive decay. They have a mass of 4 atomic mass units, which is very large compared to the mass of electrons. And they are positively charged. And then the target atoms would be a gold foil. So gold is a large atom. It has a mass of 197 atomic mass unit, and it's very malleable. So you can flatten it into a foil. And so that would be the target they use. So let's look at the gold foil experiment performed.
The mystery of how the electrons fitted inside the atom was eventually solved here in Manchester, in this building in 1911, by Ernest Rutherford. Rutherford was, in my opinion, one of the first proper particle physicists, because he used beams of particles as projectiles to explore the structure of matter. Now, of course, in Rutherford's day, there was no such thing as a particle accelerator. So he used the decay of radioactive elements to produce his beams of particles. This is Rutherford's original desk. And in fact, if you hunt around a little bit, you can detect traces of radioactivity 100 years later. Rutherford asked 2 of his students, Hans Geiger and Ernest Marsden, to fire some alpha particles at a piece of thin gold foil and see what happened. So imagine these tennis balls are the alpha particles. Now, if the atom were, as Thomson had suggested, a kind of amorphous blob, then you'd expect the alpha particles to pass right through. And that's indeed what happened. to most of them, but to their surprise they found that around 1 in 8,000 bounce right back. After 2 years of puzzling over the meaning of these results, Rutherford realised that in order for the alpha particles to bounce back, they must hit something small and dense. So his new model of the atom was a bit like the solar system, with all the mass concentrated at the centre and the electrons orbiting like planets around the sun.
Today, we know that this picture isn't quite correct. Quantum mechanics tells us that we can't know precisely where the electrons are, but we can predict that they reside in distinct shells around the nucleus.
Rutherford's alpha particle scattering experiment was remarkably direct and simple, and it showed the nature of what the atomic structure is. By the way the alpha particles bounce off the atom, he worked out where the positive charge of the atom lives.
Rutherford had come to the astonishing conclusion that most of the atom, and therefore most of what we think of as ordinary matter, is in fact empty space. So if this apple were the atomic nucleus, the electrons would be a kilometre away.
After discovering the nucleus, Rutherford continued doing experiments, firing particles at different targets to delve into the structure of the nucleus itself. By 1932, Rutherford and his colleague James Chadwick had found that the nucleus is made of two kinds of particles, positively charged protons and electrically neutral neutrons.
The discovery in these experiments of neutrons, uncharged atoms of mass 1, has proved of great significance and importance, and has given us a much clearer understanding of the actual structure of nuclei.
So in the gold-foiled experiment, alpha particles are shot by a radioactive sample, and they are shot at a gold foil. And all alpha particles are expected to go through the gold foil and be detected by the screen behind as going all through it. However, we saw that the results was that some particles went through it, but some were deflected at large angles, and some particles were completely bounced off the gold foil. So if the atom was like a plum pudding model, like Rutherford or Thomson suggested, all the alpha particles should go straight through all the atoms. But what you observed is actually that most of the alpha particles went straight through. Some were deflected at large angles, and very few didn't even go through and were bounced back. So that suggests a nuclear model of the atom. So Rutherford's conclusions was that the atoms is mostly made of empty space. This is confirmed by the more than 99% of the alpha particle that went straight through the gold foil. The atom contains something dense that was small in volume compared to the atom, but large in mass because of the few alpha particles that were deflected or bounced back. And then this dense part of the atom was positively charged because of the large deflections of some of the particles. So the electrons were pushed away by that positive charge in that dense center. So then they came up with the nuclear model. And the nuclear model says that the atom contains a tiny dense center called the nucleus. The amount of space taken by the nucleus is only about 1/10 trillionth the volume of an atom. So it's like a tiny dot inside a large room. You have to imagine the nucleus very, very tiny compared to the size of the atom. The nucleus has essentially the entire mass of the atom, so 99.9% of the mass is there in that tiny dot in the middle of a large room, which would represent the whole of the atom. Because the electrons weigh so little that they contribute practically no mass to the atom. And then the nucleus is positively charged. The amount of positive charge balances the negative charge of the electron. We have to have a positive charge to cancel out the negative charges from the electrons so that the atom is neutral overall. And so the electrons are dispersed in the empty space of the atom surrounding the nucleus, like water droplets in a cloud. So Rutherford proposed that the nucleus had a particle that had the same amount of charge as an electron, but opposite sign, so a positive sign, based on the measurements of the nuclear charge of the elements. So these particles are called protons. So the protons have a charge of +1 and a mass of 1 atomic mass unit. Since protons and electrons have the same amount of charge, +1, -1, for the atom to be neutral, there must be equal numbers of protons and electrons. But there were some problems with this new theory, the nuclear model. How could beryllium, which is atomic number 4, have 4 protons stuck together in the nucleus? Shouldn't they repel each other? Because we know that like charges repel each other, and so 4 positive charges stuck together in a nucleus is hard to believe. And if a beryllium atom has 4 protons, then it should weigh 4 atomic mass units, but it actually weighs 9 atomic mass units. So where is the extra mass coming from? Because each proton weighs 1 atomic mass unit and there's 4 of them. So that's 4 atomic mass units expected. And the electrons, their mass is so little, 0.00055 atomic mass unit, which is 2,000 times smaller than the mass of a proton. And there is only 4 electrons, so they cannot account for the extra 5 atomic mass unit of mass. So there must be something else there. And to answer these questions, Rutherford proposed that there was another particle in the nucleus, and it is called the neutron. Neutrons have no charge and a mass of 1 atomic mass unit. So the masses of the protons and neutrons are approximately 1 atomic mass unit for both of them. So in summary, the atom is made of these 3 subatomic particles: the protons, the neutrons, and the electrons. And here you have the mass in grams, and you can see that the masses of protons and neutrons are similar and very, very small if you use the grams as the unit. And the electrons have a mass that is 2,000 times smaller than the mass of a neutron or a proton. In atomic mass unit, it is easier to compare, and you see that protons and neutrons are both around 1 atomic mass unit, but the electron is negligible in atomic mass unit. You can neglect its mass compared to proton and neutron. The protons and neutrons are located in the nucleus of the atom, and the electrons is roaming around in the empty space around the nucleus. The charge of the proton is +1. Neutrons are neutral, no charge, and electrons are negatively charged with 1 negative charge per electron. And then you see the symbols and how the symbols recall the charge of those particles and their name. So since then, since the 1960s, other subatomic particles have been discovered, further smaller than the protons, neutrons, and electrons. And these are called quarks. And I let you watch those videos to discover more about quarks by yourself. There are some additional information on these other subatomic particles that we call quarks, and all these links will allow you to see more of these subatomic particles. Briefly here, quarks are what neutrons and protons are made of. And there are 6 types of quarks, and they are known as flavors: up, down, strange, charm, bottom, and top. And given that they have a fractional electrical charge of either 2/3 or -1/3, you have different number of quarks per proton and different numbers of quarks per neutrons. and it explains their difference in charge and the fact that they have the same mass or about the same mass. So you can explore more about the quarks using those slides and the links I provided earlier.